Good evening, everyone. A very warm welcome to everybody. Thank you for joining today's session. My name is Dr. Diksha Karapurkar and I run Pravinya Research. I'm a GIS instructor here, which is a geospatial training and consultancy based here in Goa. For those of you continuing from the earlier sessions of this course, it is wonderful to have you back. And for anyone joining a topic like this for the first time, don't worry, we will build everything up from the very first principles. So far in this course, we have spent most of our time on one very big question, which is where does this groundwater recharge and how do we even map it? Today, I want to widen the lens because once you have learned the techniques that we use for recharge mapping, we will realize that the very same technique can answer a whole family of groundwater questions. And this technique is multi criteria decision analysis or MCDA. Over the next hour, we will look at three very different groundwater assessments: water quality, aquifer sustainability, and urban flood risk. And you will see that all three are built from the same engine. We will go through the parameters each one uses and then we will spend real time on the methodology. This will include how we rank those parameters, how we weigh them, and how we combine them into a single map. Let me give you a quick roadmap of this hour so you can know where we are headed. We will spend the first 10 minutes or a little more on the big idea, why we combine many factors instead of just one, and what the common engine looks like. Then we will take each of these three assessments in turn, about 7 or 8 minutes each, looking carefully at the parameters and most importantly, the logic behind why each parameter is chosen and how it is scored. After that, we devote the second half of the session to the methodology itself, which will include the ranking, the weighing using the analytic hierarchy process, the overlay computation, and the validation. And we will close with a glimpse of how far this same method can stretch beyond our three examples. One thing before we begin, I want you to resist the temptation to think of these as three separate topics to memorize because they are not. They are three illustrations of a single skill. If at the end of the hour you walk away having truly understood the engine, you will be able to design assessments I haven't even mentioned today. That is the real goal. So as we go, keep asking yourself um, what is um, what is essentially staying same across all these assessments and what is changing. Now, why multi criteria analysis for groundwater? Why do we even need multi criteria analysis? Why not just measure that one thing we care about and be done with it? To this, the answer is that groundwater problems are almost never controlled by a single factor. Think about water quality. Is the water safe because the nitrate is low? Partly yes, but the fluoride might be high. The salinity might be a problem, or the hardness might make it unpleasant. No single number will tell you whether the water is good. The same is true also for sustainability and also for flood risk. Every meaningful groundwater question is multifactorial. There are always several things which are acting together. So multi-criteria decision analysis is simply a structured way of combining those several factors into one interpretable answer. We take several thematic layers, several maps, and we weigh each one by how important it is, and we blend them into a single index. That index is something a planner or a policymaker can actually read and act on. Every single assessment that we will discuss will use same 5 step engine. Step 1, we select the parameters relevant to our questions. At the second step, we reclassify and rank each parameter. We score each class from 1 to 5 according to how much it influences the outcome. At the third step, we assign weights using the analytic hierarchy process. And step 4, we run a weighted overlay for every pixel. We sum the weight times the rank. Okay, we will sum. So, weight once we assign, that will be multiplied with the rank. And step 5, we classify the results into zones and we validate it. That's it. Select, then you go for ranking, weight, overlay it, validate. These are the 5 steps. Let me give you an everyday analogy, because this idea is more familiar than it sounds. Imagine you are buying a house. You don't decide based on just one factor, isn't it? You care about the price, location, size also matters, and also the condition. In addition to this, a distance to your workplace. These are also factors. Those are your parameters. Now you score each house on each of those. That's the ranking. But price might matter more to you than size. So you weigh them. And then in your head, you combine all of that into an overall sense of which house is best. Okay? Which house is best. That is what we call overlay. A multi criteria analysis is simply doing that same process intuitively and also formally, transparently, and you also have a factor of spatial analysis in there, so that every pixel on a map gets its own honest score. The only difference between buying a house and mapping groundwater quality is the parameters and the fact that we do it across millions of pixels at once. And because it is formal and transparent, it is defensible. When, for example, a government department or a funding agency will ask you why a particular village was flagged as high risk, you don't have to wave your hands. You can show them exactly which parameters drove it, exactly what weights you used, and exactly how consistent your judgments were. That transparency is the reason why multi criteria decision analysis has become the standard approach in groundwater studies world over. What changes between assessment is only the parameter set and the ranking direction and the weights. The method doesn't change. This is the single most important idea in the whole session. If you learn the engine once, you can drive it for water quality, or for sustainability. You can drive it for flood risk. Machinery never changes. What changes is only the input. So here we have three of such assessments. Let's look at them. The first is the groundwater quality index. Here the question that is getting solved is the water safe to use? So here we are talking about groundwater quality. We take a set of these physico chemical parameters. Okay. Um, these are essentially laboratory measured from water samples, or it could also be readily available. We will look into that source as well, and we combine them into one index. The output is a map that shows you area by area whether the water is excellent, good, moderate, or poor in quality, or unsuitable for use. The second is aquifer sustainability and overexploitation risk. Here, the question is, how long can we keep pumping? This one will balance what we are taking out, the extraction and the resulting decline, against what is coming back inside it, that is through recharge and the storage. Here, the output is going to be a risk map which is running from safe all the way to overexploited. And the third one is urban flood risk and waterlogging. Here the question is, where will water pond or flood? Here we combine the shape of the land, the drainage, the soil, and how much of the surface has been paved over. Um, and here the output will be a flood risk map from low to very high. Three completely different questions these are, that is safety, sustainability, flooding, and yet, as you will see, there are three. There are uh, there are these three turns of the same handle, and which means that the methodology is same. Some of the parameters will also remain same, and we will get started. We will start with groundwater quality index. Our first assessment, the groundwater quality index, or GWQI, as you will find it in many literature. The goal here is to map the sustainability of water for drinking and for irrigation. So this is one of the most widely used groundwater assessment within India, because so much of our rural and peripheral urban population will depend directly on wells or bore wells for their drinking water, and because the quality varies enormously from one village to the next, we want to find out which areas are safer. Here are the parameters. Now, unlike recharge mapping, where our inputs were terrain and geology layers, here our our along with rainfall, other other kind of parameters that were obtained at laboratory also comes into picture. So it is not just the quality of the rainfall or the rainwater, it is also about measuring what are the different chemical parameters that are present within the groundwater from which was recharged from the rainfall. So what we do, we collect water samples from wells across your study area, and we get them analyzed, and then we interpolate each parameter into a continuous surface. Interpolation, we have learned two types, IDW and kriging, exactly the same techniques that you have learned earlier in this particular course during the second session. Then we compare each parameter against a standard in India, that is typically the BIS 10500 drinking water standards or WHO guidelines. Let me walk you through these parameters one by one. So, pH first. This is the acidity or alkalinity of the water. It matters not just on its own, but because pH controls how soluble other things are. For example, metals. For instance, these metals, they become much more mobile at low pressure, low pH. So we want pH sitting comfortably in the range of about 6.5 to 8.5. Water in that band gets the high rank. Then we have TDS, total dissolved solids, often measured through electrical conductivity. This is your overall salinity, the total load of dissolved material within the water sample. Low TDS, below about 500 milligrams per liter, is very excellent. Um, but as you see TDS climbing, the water will become brackish and eventually undrinkable. The next we have total hardness. that is mainly calcium and magnesium carbonates. Hard water causes um, scaling in pipes and utensils. If you have seen this white deposit that is found on tap and other of your um, plumbing hardware at house, essentially the steel ones, that is what we call scaling, and it affects the taste and palatability of the water. So if you have soft water below about 200 milligrams per liter, rank it higher. Then we have nitrate. This one I always flag because it is pollution indicator. High nitrate usually means contaminations from essentially agricultural fertilizers or from sewage. It is also a genuine health hazard, particularly for infants. We want nitrate below 45 milligrams per liter. Then we have fluoride. This is a big issue in many parts of India. Too little fluoride and you get dental problems. Too much and you get dental and skeletal fluorosis, which is a serious disabling condition. So fluoride is interesting. The ideal is a narrow optimal band around zero point 0.6 to 1 milligram per liter, not simply as low as possible. Then chloride, a salinity indicator, and importantly in coastal areas like much of Goa, a marker of saline intrusion. When seawater starts pushing into a coastal aquifer, chloride is one of the first things to rise. Low chloride below 250 milligrams per liter will rank excellent or will rank high. Then we have sulfate that affects taste and can also have a laxative effect at higher concentrations. We want it below about 200 milligrams per liter. And finally, iron and other heavy metals. Iron causes staining and it also causes unpleasant taste. Other heavy metals can be genuinely toxic. We want all of these below their permissible limit. Let me make the ranking idea a little concrete with a quick example for nitrates. So, suppose we decide on five classes for nitrates. Nitrates below 20 milligrams per liter, that is pristine water, we will give it a rank of 5. Then 20 to 45 will get a rank of 4. Then 45 to 100 will get a rank of 3. And then 45 sorry 100 to 200 will get a rank of 2, and more than 200 will get lower rank, that is of 1. So we have taken a continuous measurement in milligrams per liter and turned it into a clear 1 to 5 sustainability score. We do exactly that for every parameter. We have done this during yesterday's class as well, and for each parameter with its own breakpoints that are based on BIS or WHO standards, okay, to make it more methodologically sound and um, defended. So in the real world, no, you will rarely have a very perfect or evenly spaced network of these sampled wells. So you will have clusters where someone collected um, a lots of sample, and there will also be gaps where nobody has collected any samples. So this is why this interpolation step will matter so much, and why this choice between IDW and kriging is also necessary. We have covered this earlier, so uh, it is not it will not be covered again. In areas with very sparse sampling, kriging at least will give you an honest uncertainty surface, which will tell you where to trust the map less. I always recommend producing that uncertainty layer alongside this quality index, so you know which parts of your map are well supported by the data and which parts are essentially educated guesses. And one more practical note, always check your standards carefully. BIS 10500 will distinguish between an acceptable limit and a permissible limit in the absence of any alternative source. For a community that has no other water, a permissible limit will apply. For one with choices, the stricter acceptable limit should apply. So, the very same nitrate value might be ranked differently depending on the social context of who is drinking. Good groundwater science is never purely technical, it always sits inside the human society. Now, here is something that I want you to notice because it will come back later. For almost every one of these parameters, the high rank 5, goes to the value that is good for human use. Low TDS is good, soft water is good, low nitrate is good. So, for the quality index, a high final score means good water. Hold that thought because when we get to flood risk, the direction flips completely, and we will come back to that. Coming to the second assessment, which is aquifer sustainability. Our second assessment, that is aquifer sustainability and over exploitation risk. We will talk about this. The purpose here is to flag the aquifer, or really the assessment units where extraction is outpacing recharge. Now, this is the question behind India's whole groundwater regulatory framework. The Central Groundwater Board, or CGWB, will characterize blocks as safe or semi critical, critical, or overexploited. And this is done because we are drawing down many aquifers faster than they are getting refilled or getting recharged. Let's look at the parameters. And right way, I want to highlight mm, ranking direction, because here it is the opposite of the quality index. For this assessment, a high rank, that is rank 5, means high risk. We are mapping danger and not goodness like we were doing in earlier case. The areas that light up at the top of the scale are the ones that are in trouble. Okay, so notice also that this assessment deliberately includes both sides of the water balance. There are supply side parameters about recharge, and there are also demand side parameters about extraction. You cannot judge sustainability from only one side, you have to consider both, that is groundwater withdrawal and groundwater recharge. First, groundwater level decline. This is a long term trend. We have already prepared these maps. So we take years of water level data and we fit a trend, often using Mencandle test. You can read a little about it, which you may remember from our fluctuation session. So in our fluctuation sessions, we were looking at groundwater decline. So if we prepare such maps for longer extended period, we will be able to identify those areas that are consistently declining. If we have a persistent decline, which is a clear signal for a warning sign, then we will give it the highest rank. Second is a stage of groundwater extraction. This is the ratio of how much we draw out to how much we recharge. The very ratio that the Central Groundwater Board uses. If that ratio is over 100%, we are mining the aquifer. That is overexploited category and maximum risk. Third, we have seasonal fluctuation, which is the difference between pre monsoon and post monsoon levels. We have already done this during our second session. If we have a healthy aquifer, then it will strongly recover after the monsoon. If the post monsoon recovery is weak or the swings are enormous, that is, the fluctuation is more, that will signal stress. Then we have recharge potential, and here we reuse the recharge index. We build earlier that we built earlier in this particular course, um, while we were identifying recharge zones. So, an area with low natural recharge capacity is more vulnerable because once you draw it down, it refills very slowly. Then we also have aquifer storage, or what we call specific yield, essentially how much water the formation can physically hold. If we have a thin or low storage aquifer, then then it has very little buffer, so it tips into stress. It tips into stress, and we have to assign a higher rank to it. Sixth, we will talk about well density and pumping density, the concentration of these abstraction points. Where you have hundreds of borewells packed together, very closely spaced, the cumulative draft is more, and hence we give it a higher risk. Then we have land use demand. High demand crops like paddy or sugarcane, which consume a lot of water, or very dense urban demands, they will push extraction, and hence we will have to assign a higher rank to it. Then we have rainfall variability. uh, where the rainfall is low or erratic, natural replenishment is unreliable. So we have to identify areas that have more rainfall, and hence groundwater replenishment will be feasible. But if it is poor, then we will give it a higher risk or higher rank. Let me add some India specific context here, because this assessment connects directly to a real policy within India. Central Groundwater Board, together with that of state groundwater departments, they are periodically assessing every block in the country, and they place it in one of the four categories, which are based on the stage of extraction ratio. Below 70% is safe, 70 to 90 is semi critical. Um, just consider that we are ranking the stages of groundwater extraction here. So if it is 70%, then it is below 70%, then it is safe. So 70 to 90 is semi critical, 90 to 100 is critical, and above 100% is overexploited. So you are withdrawing more than nature is replacing every single year. That is exactly what it means. Some whole districts of Punjab or Haryana or Rajasthan and Tamil Nadu, these are now in that overexploited category, and water tables here are also falling by almost a meter or more every year in certain places, in fact. So this is one of the most serious resource crisis that our country faces, and it is precisely that this assessment is designed to map at a finer sub-block resolutions. Now, here in Goa, the picture is gentler. We are largely in the safe and semi-critical categories. Now, all thanks to the orographic rainfall and the laterite terrains, but it is still not uniform. Like the coastal belts where there is tourism, urbanization is concentrated, and there is high demand, saline water intrusion is also a threatening category. Because of that, we are in problem. Then all this will require constant monitoring, and that is exactly the value of a spatial sustainability assessment. So these are the kind of areas where these kind of assessments are really in demand. So it lets you find those pockets where there is a lot of stress hiding. And it also helps you identify the better areas that are under lesser stress. So a block can be identified and classified as safe on the paper, definitely, while in a cluster of village, uh, it might be running dry, um, because it is a comfortable source of water, better source of water, a lot more withdrawal. Now, um, moving on to the third assessment, that is urban flood risk. Our third and very final assessment that we are discussing is urban flood risk and water logging. Now, you might ask, this is a groundwater course. Why are we talking about flooding? There are two reasons for this. First is the techniques are identical. So it's a perfect illustration of how transferable this method is. Methodology can be used for various different assessments, not just groundwater. Please keep that in mind. And the second is flooding and groundwater. These are very deeply linked. So if we have a shallow water table, then it will reduce the soil's capacity to absorb rainwater, that is downpour, and because of which waterlogging is quite literally the um, possible way in which water table will come towards the surface because of excessive recharge. So this belongs to this particular session. So high rank here means high susceptibility, like we were discussing in the previous assessment. We are mapping danger basically, and just like how we did it for the sustainability assessment, not like how we did it for parameter where we were searching for goodness. Here we are searching for susceptibility or danger. So here the kind of parameters that we are using will be a mix of hydrological factors with that of urban form factors. For example, then we have elevation, that we are extracting from digital elevation model like srtm that we have used. Water will flow downhill and it will collect in the low ground. So the low lying areas will get higher susceptibility rank, and hence you will assign higher rank to it. Then if we talk about slope, flat terrains will drain very slowly, so water will sit there and it will pond. So very gentle or flat slopes are the most flood prone. Notice that this is the reverse of recharge mapping where flat land was good. Same parameters but opposite meaning because the question here is different. Then we have drainage density. This is the channel capacity to carry water away from that region. So, low drainage density is worse for flooding because there are fewer natural channels to remove the water that pours into that area. Now, then we have topographic wetness index. This is a beautiful composite derived from this dam that will capture whether water naturally accumulates based on how much area will drain into a point and how flat that point is. High topographic wetness index means convergent flow, wherein water is gathering and hence high flood risk. Then we have distance to drains or rivers. The closer you are to a channel, the higher is your exposure when that channel overtops or fills up with drainage water. So proximity will raise the rank. Closer the region is to a given river, higher is its flood risk. So we will assign higher rank to it. Then we have soil infiltration that is expressed through hydrologic soil group. You will remember hydrologic soil group from our earlier session. Group A will drain freely. It is highly permeable. Group D, however, will barely drain. So we will assign lower rank to it. Um, Sorry, we will assign higher rank to the group D here, and group A will get lower rank. So clay, that is group D soils, will generate most runoff because it is not absorbing anything, and so e- also it will be having higher susceptibility to flood rank. Now impervious, uh, taken from this land use map. This is urban signature. For example, you have roads or rooftops or paved surfaces. This will be impervious. They will seal the ground completely. So rainfall that would have soaked in by this soil will instead start running over the land, forming runoff. And dense built up areas, wherever they are present, you will assign maximum rank to them. Then we have rainfall intensity. it's not just total rainfall, but it is how hard it comes down. That is how fast water comes down. What is the mm, volume of water, that volume of precipitation that comes down to the surface. So a very short and intense cloudburst will overwhelm the drainage, um, and hence higher flood. Higher rank will be assigned to high intensity rainfall days or rainfall places. And finally, then we have groundwater table depth, which is wherein a very shallow water table will leave almost no room in the soil to absorb any incoming rain. So shallow water table areas will flood and waterlogging will be um, observed. So there is a direct connection between groundwater and flood. That is what we were talking about earlier. Let's talk a little bit longer on this topographic wetness index, because it is such a useful layer, um, that many people haven't even heard of it before, or you might have not read about it before. So total wetness index will combine two things from the DEM, that is digital elevation model, as to how much upslope area will drain into a point, that is how much is the area of catchment above a given point, and the local slope at that particular point. So mathematically, it is a natural log of the upslope contributing area divided by the tangent of the slope. Um, uh, what exactly is this? That is a topographic wetness index. It is a natural log of how much of upstream area is draining into a given point, and that entire area is divided by the tangent of the slope. A point that has a large area draining into it is itself um, into it, and is itself flat, will be very wet, because lots of water arrives there and none of it will leave because it is a flat terrain. Whereas a point which is present on steep ridge with nothing about it will be completely dry. So total wetness index is essentially a map of whether water wants to gather deprived purely from the terrain. Okay. That is, it will keep accumulating, um, or it will not. So it is invaluable not just for flood mapping, but also for wetland identification, also for soil moisture, or recharge studies will also be dependent on this. So you compute it in QGIS through Saga Toolbox or via this R watershed and R um, top IDX and IDX tools that are present within GRASS. You will find that in all these three assessments, no slope was appearing in all three. Soil, you have seen it is appearing in two. Rainfall appears in all three. Then drainage density and recharge, they are also recurring. But the same fundamental layers will get reused. So just rank differently depending upon what is the question that you are trying to address. Which means the same parameters that you generate, you can use it across different assessments. So once you have built a good library of these thematic layers, you can run many assessments from it. I cannot stress anymore, but this is a practical efficiency of multi-criteria decision analysis. The first assessment you might build very slow, because you're still preparing every layer from the very scratch. But the second layer will be faster, and by the time you reach any fifth assessment that you're doing, you are most likely to just go ahead with re-ranking or re-weighing layers, because you have already prepared the fundamental layer that is required. Then let's talk about the methodology. that is ranking of parameter classes. So we have met our three assessments and their parameters. Now we come to the methodology. This is the weighted analysis that we run after we have ranked our parameter classes as per the requirement. And I want to stress again, what follows applies identically to all three assessments. We are now describing one engine. Let's break it into four clear steps. So first is reclassifying and ranking these parameter classes. So first, reclassification and ranking. The problem that we are solving here is that our parameters are all measured in different units. For example, pH has no unit. TDS is in milligrams per liter. Slope is in degree. Rainfall is in millimeters. You cannot add millimeters to degrees. It is meaningless. So before we can combine anything, we have to bring every parameter onto a common scale, or what we call normalization. We do this by reclassifying each parameter into classes and giving every class an ordinal rank. So we are using from 1 to 5 here. 5 is the most favorable for the outcome that we are trying to score, and 1 is the least. So we strip away the original units and we will replace them with a simple, comparable, suitable score. We have done this previously where we were identifying recharge zones, but please pay attention. Um, one very single most common mistake that people make is getting these ranking directions wrong. So let me make this very clear with our three observations and three examples. Sorry, when we were doing the quality index, rank 5 meant best quality of water. Low TDS gets, for example, highest rank, that is 5. Optimal pH will also get 5. So in the final map, a very high index means good water. High is good. So then for sustainability risk, rank 5 means highest risk. A steep decline gets a 5. Okay, steep decline of groundwater gets a 5. And then we have mm, an overexploited extraction stage that will get highest number or highest rank. So whenever you assign a higher index, it means that it is in danger. So high is bad in this case. And for flood risk, rank 5 means highest susceptibility to flood. Flat ground will get a 5. Impervious or paved surface will get again 5. And low drainage also gets 5. Again, here high means bad. Earlier high means good. That is, water is drinkable. So you must decide before you start what your high rank is going to mean, whether it is going to mean goodness or danger, and then rank every single parameter consistently with that particular decision. If you mix directions, your final map is going to be a nonsense. This is where I see students go wrong also most of the time. So please be deliberate about it. In QGIS, the tool for this is raster. Then uh, we will use raster calculator to reclassify the classes into these ranks, that is 5 to 1. So you define the class breaks, and the rank is also given to each of this class, and uh, everything else is done by this itself. For categorical layers like soil group or land use, you will reclassify those discrete categories. For example, if it is vegetated region, mm, then it will get lowest rank for flood risk, because vegetation will absorb water, and what will happen is that the flood risk will go down. Whereas, mm, yes, that's it. Then we have weighing. Now, what ranking will do? Ranking will put all our parameters on the same scale, that is normalization. But mm, you see, it will be treated, it will treat this ranking, no, it will treat them as equally important. But these all these classes within a given parameter, they are also not equal. So in flood risk, elevation matters more than that of the depth of the water table. So in quality, you will find that nitrate and fluoride might matter more than sulfates. We need a principled way to say how much each parameter counts, and that is what the analytic hierarchy process will give us. AHP was developed by Thomas Sati in 1960s, and eh, eh, by the greatest virtue of it is that it does not ask you to assign weights directly, which is very hard and arbitrary as well. Instead, it will ask you to compare parameters, that is, two parameters at a time, which is much better for a human, rather than assigning weightage to all the categories at same point. So the comparison uses this fundamental scale from 1 to 9. If two parameters are equally important, you score 1. If one is moderately more important than the other, then you will assign it 3. Strongly more important, 5. Very strongly, 7. Then extremely, then that is 9. We will be discussing this through a hands-on session on AHP tabulations as well. So here the procedure has 4 steps. First, you build a pairwise comparison matrix, every parameter compared against each other. Second, you normalize the matrix by dividing each entry by its column total. And third, the total weight of each parameter is simply the average of its row in that normalized matrix, and um, that is what the row average is. Mathematically, the principal eigenvector, okay, that is what it is called, which is a normalized matrix. And fourth, uh, this is the most clever part. You will compute the consistency ratio to check that your judgments were logical. So there is a concept of consistency ratio as well there. We will be talking about this more when we discuss the hands-on practice on this. So the rule is simple. The consistency ratio, that is CR, must be below zero point 0.1, that is below 10%. If your uh, if your consistency ratio comes at 10% or higher, then your judgments are inconsistent, and you must go back and revise the pairwise comparison, that is, reorder them as per the highest influence to lowest influence. So don't ignore it. Whenever you build a model on inconsistent weights, uh, it will become futile, it won't be defensible. And if you are publishing or submitting to an authority, the first thing a reviewer will ask for is your consistency ratio. What was your consistency ratio when you made the changes? Coming to validation and sensitivity analysis. Now, what exactly is validation? A map that looks plausible is not the same as a map that is correct. Before anyone makes a decision based on your output, you must show that um, it agrees with the independent or observed reality. A map has to mimic that of the real environmental situation. For the quality index, for example, you validate against these measured laboratory samples that you deliberately held back and did not use in the mapping. So you, while you're collecting samples, you collect few more, so those you can use for validation and ensure that the kind of results that you're getting is reliable. You compute the correlation between your index and those independent measurements. So that will give you the validity. And you can also cross check, uh, do the areas that you mapped, um, consistently cross check, so that you know what is the deviation of your result. For sustainability, you overlay your risk map against the official Central Groundwater Board categorization of assessment units. Like there is safe, critical, overexploited, and against the documented long term decline records as well. You can categorize them. If your high risk zones line up with the officially overexploited blocks, you will have higher confidence. And for flood risk, you overlay against historical inundation reports, waterlogging complaints, high watermark reports, etc. etc. Um, a very common and rigorous approach is the ROC curve, and it's area under curve, that is AUC statistics that are computed against known flooded points. Cancel this. Which means that you have one method, but there are three outputs. We will pull it all together with this summary table. Read across the columns, and you see three different questions. That is the water safe? Is the aquifer depleting? Where will it flood? So these three different assessments, they have different parameter sets as well. Three different meanings of a rank of five: best quality, highest risk, or highest susceptibility. All of them get a rank of five. Then there are three different data types, and three different validation strategies also. Following this, we will look into the practical session of how to go about taking a parameter, reassigning ranks to it, and then going ahead with assigning, multiplying it with the weight that you receive through AHP tabulation, and then the final calculation in order to find out the zones of interest and zones of least interest.